All right. Good afternoon. Any questions? Any comments? We are talking about angular momentum. And last time we said we have three quantum numbers, N, L, M. N part, we spent quite a bit of time with all these like long calculations, and we know it's the principal quantum number and it determines the energy. Now we want to spend some time to understand these other quantum numbers, and which is going to be related to angular momentum. And angular momentum is itself an interesting topic from like a classical viewpoint, but when you make it quantum, it's even more interesting. And we introduced like commutation relations, right? Angular momentum is r cross p, and it has like components x, y, z. And last time we spent some time to calculate the commutators. Like x, y commutator gives us z, and then you cycle through. And because they don't commute, right? Lx and Ly is not, commutation is not zero. There is immediately uncertainty relationships, right? Because they cannot be measured simultaneously. But we said, so we need to find a commuting set, because that's how we determine the quantum numbers. So Lx, Ly, Lz, they do not commute with each other, but there's like a third vector we can try, which is L squared. And we showed L squared actually commutes with Lx, Ly, and Lz. Therefore, we said we can choose L square and Lz to be commuting set of observables, and try to express everything in their basis, right? And so the goal is to find a set where L squared times F is lambda times F. This is like an eigenvalue equation. And the same eigenket also gives eigenvalue of Lz. So this is the set we are trying to set up. And for that we said they are like a useful operator, L plus or L minus. We introduced this one too. And we showed this L plus or minus commutes with Lz, L squared. But its commutation with Lz also gives L plus or L minus, right? So Lz commutation with L plus or minus is plus or minus h bar times L plus or minus. And then we said we are doing the most important move, right? Suppose F is an eigenket given to us, and it's an eigenket of L square and Lz. And this means L squared times F is some lambda times F. Of course, F needs to have like labels for eigenvalues, but I want to avoid the clutter and do it at the end. And so I just put F, and Lz times F is mu times F, and the goal is to find lambda and mu. And we said let's hit on each of these equations with L plus. And the first one was easy. If L squared F is lambda times F, which means F is a solution, then hitting with L plus shows us L plus or minus F is also a solution, but importantly, a solution with the same eigenvalue, right? It's just like a one line of calculation. Hopefully you remember that. If not, you can just do it in like 30 seconds. So this is the first one, but the second one needs a little bit more work, right? For the second one, I also hit both sides, which is given to us, with L plus or L minus. On the right hand side, L plus moved through the eigenvalue because it's just a number. On the left hand side, we had to do some work. And the work was using the commutation of Lz with L plus or L minus. And we, using this commutation, wrote L plus or minus times Lz as Lz times L plus or minus. You can see this plus or minus moved to the right. Minus or plus h bar times L plus or minus. From here, this equation, we obtain this equation. And, I think this one is, should be like that. And this equation showed us Lz just write it. This thing, so the given solution, we obtain another solution because this L plus minus F is also obeying this eigenvalue equation, but the important difference from L squared, the eigenvalue is shifted. Okay. Then we introduce our ladder. The ladder was like, okay, here's the spectrum. So there's like eigenvalues of L squared and eigenvalues of LZ. By operating with L plus or L minus, eigenvalues of L squared stay the same, so they didn't change. But eigenvalues of LZ increase or decrease. Good. Then we consider the expectation value of L squared. This is the expectation value in any given state, but we considered F. And from here we saw lambda needs to be bigger than or equal to mu squared. Then this increase of eigenvalue by operating L plus should not go forever, or decrease should not go forever. There has to be an upper and a lower boundary. And then let's say we start with the top rung, right? These are, we call these are rungs, and we started wherever it is with the top rung, and our conjecture was if you operate on top rung with L plus, it should give you 0. Okay? And we said, let's say the top rung have this, let's call this top, has this eigenvalue LZ top, LZ times F top is equal to H bar L top times F top. And the question is, what about the corresponding eigenvalue for L squared? And this is what we were trying to calculate last time. For that, we express L squared in terms of this L plus and L minus, because L plus and L minus behave nicely in the spaces. And we found this. And then when we use in that equation, right, this is L squared F top, this is what we are trying to find. And this is, I chose lower signs, minus plus plus, minus plus plus, acting on F top. And I said, this is L plus, already top rung, and when you hit on F top, it should not be able to be raised anymore, it should give 0. And LZ is, okay, this is also top squared, and this is top. LZ is H bar times L top. This is what we said. Suppose eigenvalue is given by H bar times L top, and we are going to determine L top in a little bit. Therefore, this thing became top, and this one is also top. Good? And that's where we stopped. Any questions? Yes.
How do we know where top and bottom are?
Because of this, right, I calculated L squared, and L squared on the right, on the left hand side gave me lambda. On the right hand side, I have some positive quantity times mu squared. Then by my mu squared should be bounded by lambda. And mu is increasing or decreasing by application of L plus, right? And if I hit on this boundary I found, it should not be increased anymore. Good? Similarly, it should not decrease anymore either. Yes?
So we had L, LX, Ly, but L plus or minus is just its name time.
Yeah, these are like yeah, like L plus or minus are different. They are not physical operators, but they are useful. That's why we introduced them, right? Lx, Ly, and Lz, they are observable. Whereas if you combine here, this is where we introduce L plus or L minus. In a little bit, I'm going to talk more about them, but they are not physical operators. But they help us find the spectrum, because if you hit a solution, it gives another solution. Okay. Now I want to repeat the same calculation for the bottom rank, right? So let's just remember what we did. Like just repeat all of these for the bottom rank. So this is bottom. Exactly like we say, if you operate, it's already the bottom, right? If you operate with L minus, you cannot lower it anymore. F bottom should give you 0. Exactly like here, L plus top is 0, L minus bottom is 0. And now let's define an equation for eigenvalue of Lz. Now we are interested in L bottom. There'll be it's going to have like an eigenvalue. Let's call it L bottom, or h bar times L bottom, and this is going to be F L bottom, F bottom. And the question is, what is the effect of L square on the same state? So we need to find L squared acting on F bottom. What is this quantity? And for that, I'm also going to use exactly the same quantity. But here it is already bottom, and I want to operate with L minus so that it's going to annihilate. So I'm going to choose lower signs in this case. Right? So this thing means, so this equation this thing times F bottom so this acting on here is going to give us 0 because it's already bottom, and this thing we defined it, right? Lz times F bottom is h bar L bottom, and you operate it twice. That means this is h bar squared L bottom squared, and this also operates here, and it's going to give us minus h bar Lz times F bottom is h bar L bottom, and that thing means is equal to h bar squared L bottom minus 1 times F bottom. So what were we looking for? We were looking for eigenvalue of L square, and this is the eigenvalue equation. Now we need to compare the top rank and bottom rank. So in the spectrum, you remember, right? Application of L plus increases Lz or decreases Lz, but L square stays the same, right? Then this eigenvalue, which we obtained from the top, should be equal to the eigenvalue we obtained from the bottom rank. So h bar squared L top plus 1, I think it was plus 1, yes, should be equal to h bar squared L bottom minus 1. Good. So we need to solve either top or bottom in terms of the other. So there are two solutions. Either L top is equal to L, let me do it the other way. L bottom can be equal to L top plus 1, right? Smaller one should be smaller one. So this is the smaller one. This is the smaller one should be equal to smaller one. So this is case 1. But this is nonsense, because like top should be top and bottom should be bottom. Bottom cannot be bigger than L top. This case 2 is L bottom can have minus L top, and in that case this is minus L top minus 1, those minuses cancel and I have the same equation. Good. Then from now on let's call this L top to be L, then L bottom is going to be minus L, right? So the picture is something like that. You have dot dot dot. So these are our ladder. So the top is L, so this is L minus 1 all the way to minus L, so this is minus L plus 1. Good. And from L to L, from plus L to minus L, we need n steps, right? So h bar L to minus h bar L, let's call it n steps or n rungs. That means minus L, if I take n steps, I should reach to plus L. But this means 2L is equal to n, or L is equal to n over 2. Therefore, there are two cases. Case 1, L is integer, right? This n can be 1, 2, 3, 4, like 1, 2, even 0, 1, 2, 3, dot, dot, dot. Or case 2, L is, if n is 1, half integer. So this is going to be 1 half, 3 half, 5 half, dot, dot, dot. Because n is itself integer. So the integer case is going to be our orbital angular momentum, and we obtain it from rotation, that physical rotation and physical momentum. We quantized it with our P becoming minus IH bar nabla prescription. But these half integers are, especially in the case of spin, they are not physical rotations, and we are going to talk about them next time. Today, let's just postpone this. And now we have the complete picture. So this LZ times F is like something like H bar M times F, and L squared F, what we found is like H bar squared L plus 1 F, and this M goes from minus L all the way to plus L. Now we have the eigenvalues, we can also put the labels. So typically we put labels of eigenvalues, so we know which eigenvalue to pick. Sorry, this is L, so this is M, so this is L, and this is M. And as you may have anticipate, these are going to be spherical harmonics. Good?
Is about like harmonic oscillator or same thing?
So in the harmonic oscillator, we had like a different bound. In the harmonic oscillator, we had A plus and A minus, and we said energy should be bounded from below, right? But there was no upper bound. It could go forever because there is no energy bound. You can have as excited state as you want. But lower is bounded because you cannot go to minus infinity. Your energy should always be bigger than or equal to minimum of potential energy. Like, any questions? So I want to give like a nice interpretation of this result. Typically we think of this as like angular momentum. So we think of this thing to be magnitude of angular momentum. And this is the projection. Z-axis. You can see we can only determine the magnitude and also its angle with z-axis. And the picture is something like this. Suppose this is my x-axis and this is my z-axis. And what I can have is like I can have, I don't know, some, let's say like L is equal to 2, and I can do it for more. Then I can have this projection. I can have another projection. I can have another projection. I can have zero projection, something like that. This is actually L is equal to 3. I have a little bit more clutter, sorry about that. So this is M is equal to, okay, L is equal to 3. M can take values from plus 3 to minus 3. So this is 3, minus 2, minus 1, oh sorry, 3, 0, minus 1, minus 2, minus 3, right? This is z-axis. So this is xy plane. If you want, there is also into the page direction. And the magnitude here, right, you can see the magnitude is, let me write it like this, magnitude of L is square root of L square, right? So square root of L square is h bar root L plus 1. And magnitude of Z is, let me write it like this, LZ magnitude is h bar times M, and this h bar times M changes from minus L to plus L. For example, here for this one, magnitude of LZ is equal to h bar L, whereas magnitude of L is h bar L plus 1. And we see L is always bigger than LZ. And that means we can never align the angular momentum along any given direction. And angular momentum is always going to precess like this, right? This one also going to precess like this. And this one is also going to precess like that. Okay? So you have like a Z direction, and X and Y are rotating like exactly like a spinning top. Think about spinning top, right? It's all rotating, but there's also some kind of wobbling, and that wobbling comes from like the gravitational force. And the angle here, let me erase this to reduce clutter. So there's, for example, angle here, theta. It's also like it's not arbitrary, right? In real space we can have any angle, but in the quantum case, cosine theta is limited by magnitude of Lz divided by magnitude of L, and it's going to be m h bar divided by h bar L plus 1. Right? So Lz is always less than L. And this has to do with uncertainty principle, right? Our uncertainty is like delta Lx, delta Ly is bigger than or equal to, right? This is the commutation of Lx and Ly, which is going to be Lz, and we found this to be h bar over 2 Lz. And for this one, because Lz is non-zero, there will be an uncertainty in x and y. Right? And that's the meaning of this precession, because x and y are not determined, they are just, I mean, this classical picture of course is not correct, but it helps us understand this uncertainty in x and y direction. Good? Yes?
So we started with L angular momentum, not J as L plus S, and somehow we get the spin.
Yes, yes.
It is okay, but I cannot interpret how to come up with a quantum, totally quantum effect from a classical.
Yeah, exactly. That's a very good point. Right. I want to talk about this next time, but yeah, let me just repeat what you just said. That's absolutely correct. Here is what we said, right? Classically angular momentum of this, and then there's like a P here. Let's promote it to operator, and from here we obtained this algebra. But actually, from like a mathematical point of view, this algebra is more fundamental than anything else. And think about like X and P. We could actually start quantum mechanics from X, Px being having this so-called algebra, and we could build everything else on top of this algebra. And here also, like we can forget about rotations now, we can forget about physical angular momentum, and we can say, okay, this algebra is more fundamental. Suppose this is given to us, then this immediately tells us there are two cases. Here, you can have integer angular momentum or half integer angular momentum. And in the case of spin, we are going to see if you try to think about this half integer spin like a classical rotation, you crash into a wall, right? You just have like some rotation speed which is like hundreds of times bigger than the speed of light, and that's nonsense. And then from then you say that, okay, I have to forget about this classical hunger, right? This is our classical need. Since the world is classical, we think everything should have like a classical correspondence. But the quantum mechanics teaches us the other way. Everything is actually quantum, and you should try to understand classical from quantum. And if you cannot understand something quantum from classical, that's okay, right? Because that's the bigger set. You don't understand the bigger set from the smaller set, vice versa. And as far as I know, there's no classical picture of spin. And your question is yes. Then we need to forget about that.
But you said it is like more fundamental.
Exactly. Commutation relations are the building blocks of everything else. So you write the commutation relations like Lx, Ly, and that's given to you exactly what we did in this course and the previous course. And everything else, exactly that's what I tried to do. I might have skipped here and there, but that's the most basic idea. So that's not a constraint, it's just a rule, and all other behaviors follow from the commutations. Yes. But at this moment, that's correct. You have to give up on classical physics. Nobody in the world says classical physics should be the source of quantum, right? We actually know the other way. Quantum mechanics is more fundamental. The question is, how do we understand classical physics? That's the problem. And if something conflicts with classical, it's the problem of classical physics. Right? If something, like anything else, in all theories of physics, if something has a conflict with quantum, that's the problem of that theory. Right? We have no doubt about quantum theory. If gravitation has a problem with quantum, it's a problem of gravitation. Right? If anybody has a problem, they have to solve their problem, not quantum physicists. So I have one last piece of thing I want to show you, and maybe we can take a break after that. So as you can see, these raising and lowering operators are very useful. So let's try to obtain some nicer results with them, right? So I want to think about these raising and lowering ops. And what I want to find is, I want to find L plus acting on RFLM. I know it is going to increase FL by plus 1, but I want to also find the coefficient here, LM. Exactly like we did for harmonic oscillator, right? In the case of harmonic oscillator, this one was, for example, n plus 1, and this one was n plus 1. And I want to obtain the same thing here. And the second is, if I do exactly the same thing for L minus, and this should be L minus, and let's call this B. First, I want to show this L plus is Hermitian conjugate of L minus, and L minus is Hermitian conjugate of L plus. So let's show that. Let's call F L plus acting on G is equal to F L plus plus I Ly G, right? This entire thing is acting on there, and this is going to be F L plus G plus I F Ly G. Now Lx is observable, right? Observables are Hermitian, so I can carry this here, and it becomes L dagger is equal to Lx dagger is Lx, and I can do exactly the same thing here. So this is going to be equal to Lx times F G plus I Ly times F G, right? And now I can carry this I inside, but in the brass space I becomes minus I, and this shows us this thing is equal to Lx minus I Ly acting on F G, and from here, right, this is, we know this is L minus, then L plus dagger, this is the Hermitian conjugate, is equal to L minus. That's why this L plus and L minus are not observable, right? They are observables, they have to be Hermitian. Now the second piece is I want to now find this coefficient. So L so now what was I trying to do? I want to find this thing. So L plus acting on F Lm is equal to this ALm times FLm. Let's call this thing some G, and let's calculate this G bra with G cat, and it's going to be equal to L plus FLm L plus FLm, right? And now I can carry this plus to here, and it's going to be Hermitian conjugate, so this is going to be FLm L minus L plus FLm. Good? But yes.
Say the right answer should be FLm plus 1. The eigencat of the right hand side.
So this one? Oh yes, thank you, absolutely, yes. So this is, thank you, m plus 1, yes. And this thing is going to be equal to, right, L plus and L minus we already calculated. This here. So let me copy here. So this is L minus L plus. That means I have F L M, and L minus L plus is going to be L squared, right? Let's write it. So this is L minus L plus L minus. This is equal to L squared, then minus LZ squared minus H bar LZ is this thing. So L squared minus LZ squared minus H bar LZ FLM. Let me check if I missed anything here. L squared minus LZ squared minus, I missed the bar of H bar. That's it. Good. So let me push this one. Actually, let me push it down. Now this is the one I like. So this thing acting on here is going to give us h bar squared L plus 1. This thing acting on F is going to give us minus h bar squared M, and this thing acting on there is going to give us minus h bar squared M, and F, L, M are normalized, then this is going to give us h bar squared L plus 1 minus I think this one is M squared M plus 1. We check L plus 1 minus M plus 1. But what was this? This is like L plus with itself, and L plus with itself is going to be from the right hand side. This is just a coefficient, right? So it's going to be equal to A L M, which is the number. From here we find A L M is equal to A L M up to Fs is equal to h bar times this thing. Good. Then let me write these relations, which are nice and useful, and then finish it there. L plus F L M is equal to this thing, h bar. Sometimes people also write it like this. Let me show that. Yes.
Shouldn't it be square root?
Oh yes, thank you. Absolutely, yes. Thank you. So sometimes people also write this like, let me write it here. So this is L squared plus L minus M squared plus M. And you can combine this L squared minus M squared as like L minus M, L plus M, plus what remains is L plus M. And from here you can see this is L plus M parenthesis L minus M plus 1. And this way you know that when M is equal to minus L, it's going to be annihilated immediately, so that you don't have to put numbers here. And choose whichever you want. I think it doesn't matter. So this is going to be L plus M, L minus M plus 1. And this is acting on F, L, and giving us M plus 1. And the same exercise, let me show the other one too. You can obtain now very quickly. It's going to be like this. So this is minus, and this is minus. So this one is minus 1. And I think there is one more minus here. Let me check. This one, yes.
When you first wrote L squared plus L minus M squared, isn't it supposed to be minus M?
When I wrote, can you say here?
In the corner, you wrote L squared.
Oh, this one.
Yeah.
I just opened.
Minus M?
This is plus M. This one?
Why is it plus?
Because I just opened here. So this thing is L squared plus L, right? Minus, oh yes, so this is minus. This one, right? Yes, thank you. So, and this one means this is L minus M, L plus M. And so this thing is going to be L minus M. Then you take L minus M parenthesis, and this is going to be L plus, okay, good, thank you. So this is L minus M, and if L is equal to M, now I know it's going to be 0, yes. And this is L plus M plus 1. Yes, and I think this is like this, L plus. Actually, the other one, let me fix real quick. So this one is, the second one is, so this is L plus 1 minus M minus 1 So this is going to be L squared plus L minus M squared plus M. And this is going to be L minus M, L plus M, plus L plus M. And this is L plus M parenthesis L minus M plus 1. So this is L plus 1, L minus 1. Okay, this is correct. Good. So these are the set. The other, let me also write this. This is the set we need to remember. L squared FLM is going to be equal to H bar squared L plus 1 FLM, and LZ FLM is equal to H bar M FLM, and M goes from minus L to plus L. Good. So let's take a 10-minute break and continue.